Hello students, in this video we'll consider the recursion relationship for Hermite functions and how that can be used to construct the generating function for Hermite polynomials. So recall the functions hn of x, which are the sum, k goes from 0 to the floor of n over 2, -1 to the k, n factorial over k factorial, n minus 2k factorial, 2x to the n minus 2k are the nth Hermite polynomials and these polynomials over here satisfy the second order differential equation. These satisfy the equation y double prime minus 2xy prime plus 2ny is equal to 0. That's the Hermite differential equation. We proved that in a previous video. And so now, of course, what I want to do is I want to understand properties of the derivative of this Hermite polynomial. So let's do it, actually. So what will this imply? So in other words, we know that hn prime of x, let's look at this calculation over here. Let's formally do it. So formally, we're going to sum up k bigger than or equal to 0, k permissible. I'm going to put the floor of n over 2 over here, but really we're going to have to make a restriction on what that's going to mean because it won't make sense in a second here. Then we'll have a -1 to the k, then we'll have an n factorial, then we'll have a k factorial, then we'll have an n minus 2k factorial, then we'll have a 2x to the n minus 2k minus 1, then times a what? Then times n minus 2k, n minus 2k, bring the power down, and then multiply by a 2, right? So multiply by 2 like that. Excellent. And so now what's going to happen over here is that this term over here is going to cancel with this factorial over here and reduce this by 1. So it's going to be an n minus 2k minus 1 factorial, like that. I'm going to pull that 2 outside of the whole sum, but now, of course, we see that n has to be what? That n minus 1 has to be less than 2k. So really this sum, when I perform this cancellation over here, this is going to turn into what? This sum over here is going to turn into an n minus 1. It's going to turn into an n minus 1 over 2 floor. So that's important. So now we can rewrite this as hn prime of x is 2, the sum, k goes from 0 to infinity, and then what? And then we're going to have a -1 to the k, not infinity, of course. That's a force of habit. It's going to go from 0 to n minus 1 over 2. That's what happens when you're an analyst. Everything goes to infinity when you're an analyst, but that's the restriction on k. Great, like that. And then -1 to the k, -1 to the k. Then we'll have an n factorial, divided by a what? A k factorial, and then an n minus 1 minus 2k factorial. And then a what? And then a 2x to the n minus 1 minus 2k. And now this is very, very close to another Hermite polynomial. If I write this as n times n minus 1 factorial, then all the n's have been replaced with n minus 1, right? So in other words, this thing is really just 2n and then hn minus 1 of x. Beautiful. So we have a recursion relationship for the derivative of these Hermite polynomials. And so this implies that hn prime of x is equal to 2n hn minus 1 of x. Excellent. Okay? That's our recursion relationship for Hermite polynomials. And so now, of course, let me just do this one more time. What's hn double prime of x? Well, that's going to be what? That's going to be a 2n, and then a 2 times n minus 1, hn minus 2. And so now I can take this and plug this into the Hermite differential equation. So in other words, I have 2n and then 2 times n minus 1, like that, times hn minus 2, because that's the second derivative, and then minus 2x, and then times 2n, and then hn minus 1, and then plus 2n, and then hn is equal to 0. Excellent. So now all these 2n's are going to cancel out, like that, and we can conclude now that hn of x is equal to what? Hn of x is going to be 2x hn minus 1 of x, this term over here, right on the other side, minus 2n minus 1 hn minus 2 of x. Okay? Excellent. And now typically you see this written the following way. You see this written as hn plus 1 of x is equal to 2x hn of x minus 2n hn minus 1 of x like that. And so that's our recursion relationship for the Hermite polynomials over here, right? Now, recursion relationships always give us a generating function. So let's find out what the generating function is going to be. So let's write f of x and t is the sum. Let's write n goes from 0 to infinity. N goes from 0 to infinity. Of what? Of just hn. And now it's easier for Hermite polynomials to put over n factorial, and we're going to see why in a second, because if we sort of just think about what happens to Hermite's equation and we just have a y double prime minus 2xy, we see that there's going to be Gaussian functions. If there's no n over here, there's going to be Gaussian solutions to that in the first order sense. So I'm going to put an n factorial to respect the fact that there's going to be exponential solutions to this, t to the power n. And so, of course, this is just going to be 1 plus the sum, because the first Hermite polynomial is just going to be 1. The zero Hermite polynomial is 1. N goes from 1 to infinity of hn of x, and I'm going to suppress the n over n factorial t to the n. Okay, we're going to shift this sum over here, so this is going to be 1 plus the sum, n goes from 0 to infinity, n goes from 0 to infinity. I subtracted 1 over here, so I'm going to have to add 1 over here. Then I'm an hn plus 1 over n plus 1 factorial t to the n plus 1. So that's a relationship for our generating function. So this is going to be 1 plus, now I'm going to fill in what the relationship gives me. It's going to be the first sum over here, and we're going to have to be careful about these limits over here in a second, right? N goes from 0 to infinity. Then we're going to have a 2x times hn over, I'm going to write n factorial, and then t to the n plus 1 over n plus 1 like that. That's my first term over here. That's these terms over here I've replaced with hn plus 1, right? So I have a hn plus 1 gets replaced with 2x hn, and then this term over here, I'm just going to write that as n factorial, and then t to the n plus 1, like so. Good? And then what? And then plus, the next terms over here, the sum, or these are going to be minus, of course, so minus. And then we're going to have these terms over here. So minus the sum, n goes from 0 to infinity, but really it's going to be a 1. So I'm going to put that as a 1 to infinity. Then we have a 2n hn minus 1 over n plus 1 factorial, t to the n plus 1. Great. And so now let's keep writing this out over here. So let's go back up over here. So what is this? This is going to be 1 plus, now this term over here is exactly what? This is going to be a 2x, the integral of the generating function with respect to t. So this is going to be a 2x integral from 0 up to t of f of x tau d tau. And then what's going to happen over here, let's shift these indices over here and figure out what's going to happen. So if I turn this n into a 0, what will we get over here? So if we turn this n into a 0, n goes from 0. This turns into an n plus 2 factorial. This turns into an n plus 2. This turns into a 2n plus 1. And this turns into an hn. So we see over here what we're going to get. What's going to happen? Well, now the n plus 1 cancels out, and so this is going to be an hn over n factorial, then t to the n plus 2. So what's that going to give me? That's going to be a negative 2. Negative 2, the integral from 0 up to t, right? I have a 2. And then that's going to be I have an n plus 2 over t to the n plus 2 over n plus 2. The n plus 1 is going to cancel out. And then hn over n factorial is going to be an f. So it's going to be the t times, or tau rather. So that's going to be a tau, f of tau d tau. So that's going to be a tau f of x tau d tau. Okay, excellent. And so now, of course, I have an integral equation over here for this generating function. So I'm going to do the t derivative of this thing over here. So if I do the t derivative of this expression, I'm going to have f t, the t derivative of f. The t derivative of 1 is 0, plus a 2x f of x t is equal to this, right? So this is going to be equal to this. Equal 2x f of xt, and then minus 2t f of xt. Okay? And so what this tells me is that d by dt of the log of f of xt is equal to 2x minus 2t. So that says that the log of f of xt, when we integrate this, is going to be a 2xt minus t squared. So f of xt is going to be a constant which depends on x, e to the 2xt minus t squared over here. Now, I didn't put the constant over here, but let's check. When I plug in t equals 0, I have to get 1, right? So when t is equal to 0, I get 1, so the constant in front of this generating function is correct over here. So this over here is our generating function, this e to the 2xt minus t squared is the generating function for the Hermite polynomial. So this is our generating function over here. Generating function for the Hermite polynomials. So we're going to see that this generating function for Hermite polynomials comes in real handy when we're studying the quantum mechanical harmonic oscillator, because it's going to allow me to find derivatives of these Hermite polynomials and write them in terms of the Rodriguez formula, and that's going to allow us to generate orthogonality relationships and understand the connection between the ground state, the eigenstates of the quantum mechanical harmonic oscillator, and using this generating function. Thank you very much.